Hello, I'm Fabio Polizzi. I am the Chief Editor of Nature Nanotechnology, and I'd like to welcome you all to Nature Nanotalks, and in particular to this series within Nature Nanotalks that we have organized to celebrate the 15th anniversary of the journal Nature Nanotechnology. So we've asked a number of experts in various aspects of nanotechnology to join us and to share with us their perspective, their view of their field, and they've all kindly agreed, and we're very grateful for that. Today, we're talking about a topic that I am particularly been following personally in the last few years, which is nanotechnology and the environment, and specifically water and agriculture. And we have two speakers, and our first speaker is Menachem Elimelech, and he's the Sterling Civil and Environmental Engineering Professor at University of Yale. So many has been awarded many prizes during his career, including the Clark Prize for water research, the E&I Prize for protection for the environment. But more than that, is a real world expert in membrane technology. He has particularly been interested in all his career in membrane technology for water desalination, purification, and more generally for their use in the for the use of membranes at the water energy nexus. I have heard many speaking a few times, and I've always appreciated his constructive, critical approach to research and to this field in particular. And I'm sure that it will be like this today as well. So many thanks a lot for agreeing to be with us. And well, I'll leave you the floor. Thank you.
Okay, thank you, Fabio, for the introduction. And I would like also to thank Fabio for the great work he has done in the past decade for Nature Nanotechnology. And I wish him the best of luck. Those of you who are not aware, he will be the chief editor of Nature Water, a new journal. And again, this is the subject of my talk now, membranes at the water energy nexus. So let's start with global water scarcity. Again, we know that there is climate change, and climate change exacerbates water scarcity. Let's look at this map from the New York Times, and pay attention here for my laser, the year 2020. This presents the world water stress projection for 2020, which is where we are now. And the darker the color, it means it's really severe water stress. So let's now move for 2030. You see there are more, dark area, and 2040 much more. So water scarcity is expected to really grow with time. Now let's look at the water in the world. Again, this is a nice map for the USGS that illustrate if you take all the water in the world, everything, including ocean, you can lump them into big sphere that you see here, which would be 860 miles in diameter. Now, if you take only the fresh water, not the seawater, and including ice caps, it will be a sphere that you see here, roughly around Kentucky, USA, again, and of 170 miles diameter. And if you take only the fresh water, not the ice caps, lakes, rivers, and groundwater, you see this very, very small, tiny sphere around, I think, Georgia, Atlanta, of only 35 miles. So although water covers 70% of the planet, really only a small portion of it, as you see here, 0.01% is available. Now, we also have severe water contamination or water pollution. Again, freshwater resources are polluted by many toxic contaminants, mostly anthropogenic. It means human-made. And we see that we have a dual problem, not only that we don't have enough water, but now we also don't have safe water or clean water. So this is a quite serious problem that we have. Also, we know that water, energy, and food are linked to each other. We call it the water, energy, food nexus. For example, to produce water or to treat wastewater, we need energy, like in desalination or wastewater treatment. To produce power or energy, also we need water. You know, water is a major component of all power plants. And of course, we need a lot of water for food and agriculture. So if we have any impact on one of these parts on water, it will impact energy and food. So they are interlinked and we need to remember it. So what I would like to start first about the efforts for a nano-enabled water treatment, and I would like to highlight a Center for Nanotechnology Enabled Water Treatment. We call it NEWT. Again, just a few slides about it, because I'm a member of this center. It's a center that's supported by the US National Science Foundation for 10 years. We are in the 6 or 7 years now, and it's a $40 million investment. There are 4 universities that are listed here, and many industrial affiliates that you see, a lot of companies that are interested in water. And as I mentioned, 4 universities, the center is at Rice, but Yale, University of Texas El Paso, and ASU. And the focus of this center is nano-enabled water treatment, and specifically on small decentralized system rather than this large centralized system, either for drinking water application or for industrial wastewater treatment. So here I would like to highlight a perspective article in Nature Nanotechnology that was written by several people from NEWT, as you see here, from the different universities. And we describe here the water treatment objectives, starting from the basic one, to remove pathogens. Again, if you drink water with pathogen, you can really die. And to advance one all the way to removing salts like in desalination, or to remove some trace organic contaminants. And as you see, this x-axis describes the socioeconomic capacity of the country, the region, and we see some kind of a trend. For the basic treatment, again, you don't need a lot of investment. You just put some chlorine and you can have the water safe. But if you want to remove salt by desalination or some small toxic organic contaminants, you need much higher institutional capacity or socioeconomic capacity. On the right-hand side, you see treatment technologies applicable to each of these categories. And here we highlighted in blue ones that may be nano-enabled, like for example, for salts, removing salts, we will have some membranes for desalination. For removing toxic chemicals, we will have a photocatalytic nanomaterials, membranes. And for oxyanions, we can have some, again, selective sorbents and etc. So in 2018, Fabio, the chief editor, and Wenji Sun, the associate editor, organized a special issue, or they call it an insight. This is August 2018, that focused only on water, and they had several perspective articles there and some review articles that are highlighted here. Again, this article, again, I mentioned earlier, another article by NEWT focusing on materials for advanced oxidation, and another review that focused on the risk of nanomaterials in water, in drinking water. So here are some representative NEWT, and again, our center-related articles in Nature Nanotechnology. Again, some article that you see here on desalination, how to use HBN, hexagonal boron for desalination. Here about sustainability of nanomaterials that use in water treatment, and here's some coagulations, and some other perspective articles that I mentioned earlier that you see here. So this is also sort of like to talk about the efforts on nano-enabled water treatment, but my talk will focus on nano-enabled membranes, or for desalination and water purification. And I would like to go through these slides here, images that show roughly the outline of my talk. The first part, I will talk about ultra-high flux membrane, an effort that was from 2006 until about 2014. An effort that started about 2012 deals with ultra high water salt selectivity. Again, this is ultra-high water flux. This is water salt selectivity, how we can get very selective membrane that let only water go through and not salt. And again, there's still active research nowadays, and more recently, just starting recently, and again present in my opinion in the future, will be ion-ion selectivity. So let's start with the first one, ultra-high flux desalination membranes. So again, membranes play a very important role in desalination, and again, the leading technology for desalination by far is reverse osmosis. Again, this is the scheme of the reverse osmosis plant. They take some water from the ocean, go through some pre-treatment, and the main stage is the reverse osmosis, RO, that you see here. And here we use thin film composite polyamide membranes. These are the state-of-the-art membranes. They were developed in 1980, and since then, no one was able to get a better membrane than this over 40-year-old membrane, polyamide membrane. So this is the membrane that we need to beat if you want to use nanotechnology. So as I mentioned earlier, again, there was some exciting research fundamentally about transport of water in carbon nanotubes, or in atom-thick graphene or two-dimensional graphene, and they found a very, very high water flux. Again, for example, in carbon nanotubes, they are very atomically smooth, and there is a very large slip length, and we get water flow that is, 1,000 times higher or even more than what you predict based on the Hagen-Poiseuille equation, just based on hydrodynamics. And again, some of these scientists and others in the news media promise a quantum leap in desalination. And the rationale was, if you have high water flux, you will need much less pressure, and then you can reduce the energy consumption dramatically. So I would like to say a few words about these efforts. And again, there were many papers about it, as you see here, plenty of papers in all these right journals, and even in 2017, based on a paper in Nature Nanotechnology, the BBC wrote some news. A graphene-based sieve turns seawater into drinking water, and highlighting that this technology will be, again, amazing and will desalinate water with minimal energy input. So, as I've said before, and I will highlight it later, this is an exciting area of research. Again, all this flow in these very, very small channels or two-dimensional materials are quite exciting. A lot of fundamental phenomena that I will mention earlier. But unfortunately, when you apply it for the energy of desalination, the impact is practically negligible. And I would like to show some simulations. And again, we pushed this idea from starting from 2011 until recently. If you think about the energy consumption in kilowatt hour per cubic meter versus the water permeability of the membrane, as you see here, current membranes, the permeability of the polyamide membrane that I mentioned is about this range. And as you see that the energy above a certain permeability doesn't change a lot. So you don't need to go to these very high permeabilities because you will not reduce the energy. And the story is very simple, that the energy or the pressure that you need to apply is not controlled by the resistance of the membrane, but rather by the osmotic pressure of the brine that you have within this membrane module. So this was a conclusion, and again, it was a switch in research, which led me to the next topic, water salt selectivity, or how we can get very high, salt rejection, or much more water going through compared to salt. And this effort is still going on, and I would like to highlight a few things. And again, if you look generally on describing membranes, you describe it as a selectivity. In our case, selectivity for water. So the higher, it means more water will be more selective to water. So you can think about it, very, very, very high salt rejection. And this is the water permeability. And usually the data fall with this range. We call it the permeability selectivity trade-off. If I want to have high selectivity, I also sacrifice the water permeability. So what I showed you earlier in the previous discussion, that there is minimal impact of increasing the water permeability. And what we are suggesting that probably there is a better need to increase the water selectivity, or very, very high salt rejection. And in 2016, we have written a review article that summarized potential membranes that can be used to achieve high water salt selectivity. Specifically, you can think about the protein channels like the aquaporin, carbon nanotubes, some synthetic channels that try to simulate the natural protein channels. You can think about two-dimensional graphene and some other polymer-based, surfactant-based materials. And as usual, again, there were plenty of articles that talking about the ability of nanomaterials, these are about graphene, to sieve and remove salt. And again, the objective now is to remove salt. And some other materials like molybdenum disulfate that you see here, also how we can use them to remove salt. Now, what I said earlier, these nanomaterials are an excellent platform for studying fundamental phenomena under sub-nanometer confinement. You can study about ion sieving, dielectric effects, slip length, and many, many phenomena that do not occur in the bulk, but they are very unique in this very, very small confinement. Some example, again, I will highlight the work that was done in the UK, in the Manchester group. These are, for example, in 2016, molecular transport through capillaries made by atomic scale, with atomic scale precision. These are the 2D graphene that are assembled by van der Waals assembly, and you can study a lot of phenomena here. You can think about more recent, again, papers in hexagonal boron nitride, and this is to study the transport of hydrogen through atom-thick graphene, or HBN. And again, very, very interesting phenomena fundamentally that you will not expect occurring. You think this will be completely impermeable for solutes, but protons can go there. And more recently, molecular streaming in angstrom scale channels of graphite, as you see here in this article a few years ago. So these are really amazing fundamental phenomena, but some also suggested that you can use them for desalination and get membranes with ultra high salt rejection. And I would like now to analyze and show you some work that was done by, again, led by my graduate student, Cody Ritt. And we try to model these two-dimensional graphene membranes. And we say, okay, let's try to construct by Monte Carlo these membranes. You take different graphene nanosheets, as you see here, of different size. And what's important is the coverage, the areal coverage that you see here. And then sequentially, by random sequential deposition, we build this membrane. And again, what's important now become the coverage, the areal coverage. You need to have high areal coverage and the thickness of the membrane. You expose it or subject it to ions, sodium and water. And then you measure what's coming out, I mean, by simulation, what will come out. And this is just to test the performance of this membrane. And what you see here, these quite crowded graphs, I will guide you. Again, this describes the water salt selectivity, or as you go higher, higher salt rejection. And this is the water permeability. Let's take 50% areal coverage, for example. As you build the layer, become thicker and thicker, then it's more difficult for the water to go through, and you get less and less water permeability. We stopped when we got to a minimal permeability of 1 LMH per bar. And here you see that the rejection of salt was only 10%. Let's go to more realistic. Some studies really were able to get 75% coverage. And as you build the layer, you get less and less water permeability, but at the same time, you get more salt rejection. And we stopped here because the permeability got very low because it's very thick. And we got quite high salt rejection. And when you go to 90%, no study so far was able to get 90% coverage. We still see, again, you can get, we stop here because the permeability of water become very low, and you got, quite high salt rejection. But when you look at the current polyamide membrane, which are the state of the art, we see that they have quite much better in terms of performance than these membranes. And again, these simulations were done under ideal condition, that you build a layer nicely with everything is horizontal, and the reason why you get this, you never can get super high salt rejection, as you see here, is what we call framework defects. They dominate the transport in two-dimensional materials. And again, you can think about, if you have one layer here, you cannot, even if you get 80% coverage, there will be some holes. And then there will be what we call interconnected framework defects. You really need to get a very thick membrane to eliminate these defects. But once you get a very thick membrane, then the water permeability drop below a certain value, which is not usable. So this tells you, again, defects are important. And I would like to show you another work by Xinglin Lu, who was a postdoc in my group, and now is a faculty at the UTSC in Hefei, China. And this is, we took molybdenum disulfate, we created the membrane by the method described in the literature, by deposition, vacuum filtration. We create the MOS2 membrane, and we tested the rejection of this membrane for salts and dyes. And we see quite interesting results. Again, when you talk about salt rejection, we got 0 salt rejection, and I will explain why later. And we also tested the support layer. We put this molybdenum disulfate on a PVDF support, which is a more ultrafiltration with quite large molecular weight. Now you see what's interesting. When you look at the dye, we get 99% rejection by the membrane, but the support layer that is large pore that should not remove any of these dye, you get 96% rejection, which was quite surprising. But when we analyze the dye, and again, we looked at it, you see that dyes aggregate. And if you look at this distribution of the size, you see that these dyes molecule aggregate, and this is why you get high rejection, which casts doubt about some of the other studies that use dye and reported amazingly high rejection. And we think that this dye aggregation is very, very important. We suggest to do some other materials like polyethylene glycol and other some probes, again, that will not give you this nice color for publications, but will be more accurate. Now let's go more into this, why we did not get a good salt rejection. So again, this is the membrane that we created. We did some 2D XRD patterns, and we see meridional patterns here that indicate generally that they are aligned horizontally as we expect. But if you look at this pattern, it's also indicated that they are not aligned perfectly. So we expect them to be something like this nature. They are not well aligned, and water will go through these defects. Water and salt will go through these defects. Just to prove it, we took a MOS2 crystal that we buy commercially. It's done by vapor deposition, well defined. And when we took the 2D XRD, we see a very, very different pattern, which indicate that they're supposed to be aligned, as you see here. And indeed, again, this is what we think happening. I mean, for our membranes, just all these imperfect orientation and stacking created these preferential pathways in which the salt went through. Just to prove it, again, we also took some SEM of these membranes and the crystal. And indeed, this is our membrane, the cross-section SEM. You see they are not well oriented, as opposed to this crystal, which again, based on this XRD, show you that they're very, very sort of like almost perfectly aligned. So we see that defects are a major challenge. It's a daunting challenge, and again, it will be with us. And unless we solve this defect issue, we will never be able to get these materials to perform well. And this is just from the literature. Again, if you look here, you see some kind of quite wide openings that tell you that they are not aligned well. And again, you see that it's not straight aligned. Here's another study that shows some defects from another paper. And this is our study on the molybdenum disulfate by Xinglin Lu. As you see here, you see that they are not oriented. So to summarize this part before going to the last part of selectivity, what are the challenges of nano-enabled desalination membranes? I believe, and what I think, the current approach that we have top-down approach, that you already take the existing structures and try to deposit them and make them some of membrane, they will not work because it's impossible. I mean, unless you do simulations, and like what I did in the Monte Carlo, it's impossible to align them experimentally completely. So we think that these are likely to fail. And what we suggest, we need new bottom-up molecular design. So we can design nanostructure by molecular design that you start with molecules and bottom-up build these channels. If you already take existing channels, it just will not work. And I saw you, and there were plenty of efforts and hundreds of millions of research investment. And again, you'll see more papers about it, but it's very challenging. So we suggest bottom-up approach. And also, I think for these membranes, if they will be ever, good, and to some degree, I also suggest to seek applications of nano-enabled membranes, not where polymeric membranes excel. For desalination, the polyamide is already doing a good job, but some other applications like, for example, organic solvents or applying membranes for petroleum to replace distillation and try to, molecularly separate components in petroleum. Polymeric membranes fail there, and this is maybe a fertile ground for future research. So I would like now to move to the last part of my talk. I will talk about ion-ion selectivity. And again, I talked about ultra-high water flux, water-salt selectivity, and here I will talk about ion-ion selectivity. So ion-selective polymeric membranes are important at the water energy nexus. I described earlier the meaning of the water energy nexus. For example, in water treatment, we have electrodialysis membrane that you need to use cation exchange membrane and anion exchange membrane, and we need to make them very selective. Just cations will go here and just anions for the anion exchange membrane. In nanofiltration, we wish to have a membrane that can be very perfectly distinguishing, for example, between monovalent and divalent salts, and we still cannot do it well. At the energy side, the energy conversion and storage, we know that fuel cells and electrolyzers, and they use proton exchange membrane, and also we need to tailor the selectivity of these membrane, and also, of course, make it cheaper, because nowadays they're quite expensive. And the same thing with redox flow batteries. So they need some selective membranes. We also need a critical need for ion selective membranes for the circular economy that we all talk about. For example, we will need a lot of lithium, because there will be battery storage, and lithium is the leading method. And as you see here, if you have lithium brines, we need to separate the lithium from some other ions that are roughly about the same size. So the question, how do we separate between lithium and sodium? So this will be very, very challenging. They are very, very close size. You can think about lithium-ion battery recycling. You can take the electronic waste, digest it, and then separate, lithium from other metals like that you have there, like cobalt, manganese, and nickel. In the wastewater treatment, we can think about recovery of some important nutrients like nitrate and phosphate, and we may think about selective membranes that do this job. And electronic waste, again, you can, in principle, again, there are many metals, again, divalent and trivalent metals that can also have potential to be recycled. So if we have selective membranes, we can do the job. So unfortunately, again, I'm going to show some part that, again, worked by my former postdoc, Razi Epstein. He's now a faculty at the Technion in Israel. And unfortunately, current polymeric membranes cannot do this selectivity, highly selective, job that I was referring to, because their mechanism of separation is simple, either by size or by charge. I say simple, but again, relatively not sophisticated. And you cannot, because of the structure of the polymeric membrane and this mechanism, you cannot achieve very high selectivity. So what we suggested in this perspective article, again, in Nature Nanotechnology, is really to learn from the biological channel, and specifically the potassium channel. The potassium channel is an amazing filter that was evolved in evolution of 1 billion years, and it does an amazing job of distinguishing between potassium and sodium. This is the structure of this filter. The selectivity filter is only 1.2 nanometer, very, very thin, very, very, very narrow opening of the channel, almost just enough for water molecules to go through. And the way it works, again, this potassium channel can pass 1,000 potassium ions for each one sodium ion that pass. So again, selectivity of over 1,000, which is amazing. And the way it works, again, you think about the potassium, it comes to a narrow channel, and you need to dehydrate. You know that ions can dehydrate when they want to enter a small opening, but there is some energetic penalty. Once you are dehydrated, the ion is high energy, it feels uncomfortable. So you need to find something to stick to compensate for the fact that you lose the water molecules. And the potassium channel has the right groups here, oxygen-containing groups that bind to the potassium, and the potassium feel good. Now I feel like I have some water molecules around me, and moving from side to side by hopping. and the sodium cannot do it. It just cannot, it doesn't fit here, and cannot go through this hopping mechanism. So we suggested, again, in this perspective, to really design membranes in the future, sub-nanometer channel membranes, by these principles that are really taken from the potassium channel. We need to have a size of the pore big enough, so I mean small enough that it will be smaller than the hydrated size of the ion, but larger than the dehydrated. If you dehydrate, you need to get in, so it should be larger than the dehydrated ions. Secondly, we need to have the right binding sites as indicated to compensate for the penalty, energetic penalty of dehydration. You need to have a thin layer. The potassium channel is only 1.2 nanometer, very, very thin, because if it's become very thick, then the rate of transport of the potassium will not be high. So we need to have high rate, or if you can be thinner, again, it's impossible to make it less than 1.2, but suppose you make it 0.2 nanometer, then probably it will not be selective, and also the sodium will go through because it's already the size or even smaller than the size of the sodium and potassium. And another mechanism that probably will be very difficult to implement in membranes, it's what we call the knock-on effect. Again, the distance between the group in such a way that the potassium pushes the other potassium by electrostatic repulsion, and also here. So these are amazing mechanisms that were evolved over a billion years of evolution, and the question how we can really apply them to membranes. And I would like to show you some efforts that we have done, and I'll highlight the work that was done mainly by Ryan Duchesnois. He's a PhD student in my group at Yale, and we created a polymeric membrane with again selective immunodiacetate group that you see here. So we created a layer by layer in which you take the first layer will be PAH, which is a positively charged. Then we created another polymer, synthesized another polymer that will have immunodiacetate group that you see here, deposited it here, and then another layer of PAH and another layer, and so on. So now we have a layer in which we have sites that are very, very specific for metals. There are, coppers like to bind very effectively to this immunodiacetate, and some other metals. And we did some DFT calculation to calculate the binding energy to this immunodiacetate. Again, it's binding mostly to these two carboxyl group, not a strong binding to here to the nitrogen that you see here. And we see copper has a very, very strong binding energy. Magnesium has the lowest binding energy, and you see here some kind of other binding energy. So now we wanted to study, and we wanted to illustrate the concept if we can get something close, again, not close even, resembling how the potassium channel does it. And we wanted to study the study of, transport, for example, of copper and magnesium. So these are the channels with the immunodiacetate, and we hypothesized that there will be two potential mechanisms. One of them we call site inactivation, in which the copper binds very, very strongly to the immunodiacetate. It doesn't just stay there. And this is the weaker binding ion, like the magnesium, for example. And the other mechanism, we suggested that there will be some binding, but then, come off, and then hop to the other side and come off, etc. And what we speculated that here we will not have any selectivity because this is bound here, and then the rest will just go through, and there will be no selectivity. As opposed to this case, which is resembling the potassium channel, we speculated there will be quite high selectivity by this hopping mechanism of copper, which will not happen for the magnesium because it doesn't bind strongly to this immunodiacetate. And we wanted to demonstrate it. So let's take the copper and magnesium just to recap. Again, they are identical in the size, as you see here, ionic size, but much different in the binding energy to the immunodiacetate. We studied the diffusion of this salt through this membrane that I mentioned earlier by a diffusion cell in which we have the salt here, and the receiving solution that you measure the concentration of these ions. And we did now single salt experiment. We said, let's take only experiment just with copper, and we measure the flux. So again, this is the concentration versus time. And copper doesn't go a lot because it's binding strongly to the immunodiacetate group. Magnesium bind less and it goes faster. So we see here, if we think about copper magnesium selectivity, the flux of copper is lower than magnesium, so the selectivity is less than 1. But again, selectivity doesn't mean anything if you have single salt experiments. Let's now do multi, that we have both of them. Again, this was single salt experiment that I showed you earlier. Let's do now multi-salt, in which you have the same concentration of copper chloride and magnesium chloride. And we see beautifully here that we can really get the behavior of the potassium channel. Copper goes much, much faster than magnesium because of this hopping mechanism when both of them are in the solution. And we get an amazing selectivity of 60, close to 63. So this hopping mechanism is quite important. And I don't have time to show you, but we did it for the other ions. And we found that the selectivity correlates to the difference in the binding energy between the copper and the other ions. So again, here we have the largest difference in the binding energy. We got selectivity of 62, but if you take copper and nickel, the difference in the binding energy was slower, if you remember the graph of the DFT calculation, and we got lower selectivity. So we can see that we can tune the chemistry and try to mimic the hopping mechanism. I have a few more slides. Again, I have a few more minutes to finish. So these were polymeric membranes, and polymeric membranes may not be the ideal for selectivity because we will have what we call a trade-off. Let's take an example of these anion exchange membranes that distinguish between chloride and sodium. So again, we need to have chloride going through, but not sodium. These are anion exchange membrane. And here I'm describing the selectivity versus the conductivity. Again, we need also to have high conductance. And as you see, when we have high conductance, and usually it correlates with the water content or the swelling, if you get higher conductivity, which is also desired, you will get low selectivity. And if you want to have high selectivity, we usually get lower conductance. So this trade-off is because of the dynamic. Again, it's difficult to explain, but again, there are many mechanisms. But we think about the dynamics, the nature of the polymer. There are thermal motion, and it's not fixed channel in size. It's breathing and fluctuating all the time. So what we suggest, and again, as a possibility, we can take maybe porous crystalline materials like MOF, and MOF are quite exciting materials for fundamental research. Again, they have metal node, organic linker that you can even tune the chemistry of the organic linker. And you have these cavities, and you can tune the cavities all the way from sub-nanometer to a few nanometer. And if we can design a membrane that the ions will go through this, cavity, which is fixed because it is crystalline material, doesn't have the polymer dynamics that we mentioned earlier. So if we can form a rigid, water-stable, defect-free MOF, this can be suitable for selective membranes. And I say if, but this is very, very challenging. And this brings us again to the defect. Okay, these are very, very small entities, but when you create a membrane, this is what you get. And getting a defect-free thin film with MOF or other crystalline materials is very challenging for the reason I mentioned earlier. Again, here we will have defect from grain boundaries between the crystal facets. You can have maybe poor substrate coverage, missing ligands nodes, cracks, pinholes, and stability in liquid. Once you put it in water, it's very, very challenging. So again, we're going back to the defects, which will be a challenge for all nanomaterials that are used in water treatment. So to conclude, nanomaterials can provide a nanofluidic platform, and again, an outstanding platform for studying fundamental phenomena such as ion sieving, dielectric effects, slip length, and many, many, many more, as I mentioned earlier. Defects represent a daunting challenge in the upscaling of nano-enabled membranes. And what I'm preaching for, we need a bottom-up molecular approach for creating these defect-free nanostructures. So you cannot just take the existing nanostructures and deposit them, because you will have some challenges that I mentioned. And also, again, part of the discussion, again, I know it's a talk for the Journal of Nature Nanotechnology, but again, there is always a debate. Which one will do a better job? Will molecular science or nanotechnology will be a better job? And I will leave it for the debate, which will go on probably for another many years to come. So this is sort of like a question. So at the end, I would like to thank the people who did all the work. I highlighted some of them, and this is my group and some of the funding agencies. Thank you so much.
Thank you, Manny, for this enlightening talk, as somebody has already commented on the chat. And you know, I said at the beginning that you have a constructively critical approach, and I think you confirmed my expectation, which I take it as a big compliment, by the way. I think this is a very, very sane approach to research, so, and to nanotechnology in particular. I want to remind all the audience that you can ask questions. There's a question box you can use, and I will just start with a general thing, because it's about the message that you gave about the use of nanotechnology membrane. Just a clarification. So you were referring to the possibility of, you know, building membranes for the bottom up, so not using the existing channels that are full of defects, but you know, building new membranes from the bottom up. But do I understand correctly that you are saying that even in those cases, it's probably better to focus on specialized technologies that are in which, you know, in which polymeric membranes are not working particularly well, or by building from the bottom up, maybe we have the hope to do even better than polymeric membranes?
Yeah, it's a good question. Again, thank you for the comment before. And again, I should be very brave to challenge nanotechnology with the chief editor of Nature Nanotechnology. But again, I think, again, I was referring just for the purpose of salt removal and water permeability.
Okay.
If we want to beat the polyamide membrane, probably we need to have a molecular approach, which also the polyamide are prepared by molecular approach. Now, there may be some other application for nanomaterials. Again, I focus only on desalination and water purification. But I think it's very challenging to beat this polyamide membrane. And again, we should continue with these efforts, but better to challenge the effort, as I said, to some other application in which polymeric membranes will not excel. For example, you can take atom-thick graphene with this idea of having some punching very, very nice holes, very selective, and use them, for example, in distillation for petroleum, rather than using it by, you know, you can use it as a membrane to separate molecules rather than distillation, which is energy intensive. So we should think about some other application. The desalination, again, reach a saturation in a way that what you can do for the remove it, improve it, and the improvement will be incremental. So better, I think, worthy of the investment for the other application, although you should continue with a bottom-up approach.
Okay, thank you. There are questions coming, which is really good, and I will start. Some of them are quite specific, but I think it's interesting to go over them. So, how could one characterize a silicon nitride membrane for its sensitivity to pH?
How to characterize?
Yes, I'm not sure that.
I mean, again, I did not talk about. You talk about silicon nitride, or?
Yes.
I did not talk about any such membrane like that. I talk about the hexagonal boron nitride. And again, as you know, pH will affect anything. If you want a stable membrane in water, again, there are functional groups. The pH will affect the speciation of the deprotonation and may affect the stability. But again, I think this question is quite vague.
Okay. So another question was how is the ion flux in Ryan's work when you compare it? How is it compared to other works?
The ion flux so far is relatively slow, or the rate is slow, again, because the membrane is relatively thick. And our challenge now is really how to make it thinner and getting high flux while keeping the selectivity. So again, we always have the permeability selectivity trade-off, and we are working on how to fix this trade-off. But currently is not high, but again, compared to what? Again, there are not many membranes to use to separate metals. Compared to liquid membranes, I mean, our rates are even higher. Again, the liquid membranes are the ones that are used nowadays, so are comparable or slightly higher. But like in anything, selectivity and permeability, you need to balance the trade-off, and this is the challenge. And you need to make the membrane thinner.
Okay, there are too many questions, unfortunately, to answer now. So I will, if you don't mind, Manny, I will send them to you by email. But in the meantime, I'll just ask one last one. I just choose this one because it's got to do with one of the issues that very often there's seems to be a difference in the goals or in targets or even in language sometimes between environmental engineers and material scientists when we're talking about membrane. So this is not a general question of that type, but there's a question that says yeah, so it's not a question, it's more like a comment that many of the material scientists do not know the concentration polarization, and this is what perhaps one of those issues. It's a bit of a, sorry, I'm just looking at the time and I realize that perhaps we have to leave it at that. I had also once on my own question. I'm sorry to dominate over my own attendees, but again, going back to when you said about the use of nanomembranes, particularly 2D materials. You were talking about certain specific applications. I was also wondering, I mean, I know some works in which, and I think the one on the boron nitride that you mentioned in a way is like that, but also there's a work that we published a few years ago from the group of David Jasby, in which carbon nanotubes were integrated in a polymeric matrix. And I was wondering to what extent is the role of these nanomaterials instead is not necessarily to be the main membrane for desalination, for example, but to be part of an entire device, but not necessarily as the active membrane, but as as an element to provide advanced membranes overall.
Yeah, this is a good question, I think. So when you come to when it comes to polymeric membranes for desalination, specifically reverse osmosis, they are designed in such a way that you have this right module, and it's very difficult to redesign them to add some other. For example, you can think about adding some nanomaterials and connect them to some voltage to clean the membrane. But because you pack them in such a way by spiral wound modules, and they're already very, very cheap, this is the key, cost. It will be very difficult to create new modules just for the benefit of, for example, cleaning the membrane. So the membrane companies found a way that they, every 6 months, they stop, they clean the membrane with chemicals and move on. There are some niche applications for some other emerging technologies, and I think you're referring to membrane distillation. And if you can find a niche application for membrane distillation, then such application may find a use, like the boron nitride to hit the membranes. But again, the share of these thermal technology is very, very, very small, usually in the very, very, very high concentration brines. And in that market also, we have some other technologies that are also quite effective, mechanical vapor compression. So again, there are many things that you know, in nano and membrane that can find some niche application. So, but there will not be the mainstream to replace desalination membrane, as what I mentioned. This is my point. And nothing wrong about niche. Niche, I mean,
No,
nothing wrong about it. We always have our niche.
And there's nothing wrong with the fundamental studies that you refer to, by the way. That's
I
guess
key, yeah.
one of the comments that I could make, and I don't know whether you agree or not, and perhaps in those fundamental studies, when authors write those papers, they should really focus on the fundamental studies without maybe overclaiming about their practical utility, because the fundamental studies are important themselves. They don't have to. They don't necessarily have to have that end application, that end number or the end efficiency as a reason for a paper to be published, right? So
Yeah,
maybe it's a question of trends and
I think
habits.
exactly. I think it's a very, very important point. And you, as a trained biophysicist, I know that you also, the paper that you select for your paper journal, I mean, usually have a lot of physical insight, which is very, very important, as opposed to some material based that just say I can make another piece of material without explaining it. So the fundamental understanding is the key. And I think from these nanofluidic devices that created by these materials, we can learn a lot what's happening inside the polymeric membrane. For example, what's happened to the dielectric constant inside the membrane, and a lot of other phenomena. So we can learn so much from these nano-built devices to explain phenomena in polymeric and other commercial membranes. So I fully agree with you that there is no substitute for fundamental, and I should not tell you you're a physicist and this is the bread and butter for physicists.
Yes, well, I don't feel like I've been a physicist for many years, but but okay, I suppose once a physicist, always a physicist, right? So, but thanks again, Manny. It's been really, really interesting, and as always, and I'd like to thank you for the support for the journal as well in the last few years, and I'm hopefully we'll work, we collaborate again in the future. But thanks again for today.
Okay, thank you much, everyone. Thank you. Bye-bye.
Right, and I apologize to the audience again for prevaricating them a little bit. Before I move to the second speaker, I wanted to just show you if I manage to if I can share my screen. Okay, so hopefully you can see my screen now. So as I mentioned before, this is the talk today is part of a series that we have organized to celebrate our 15th anniversary. You can still register for the other webinars. There will be the 10th, on the 17th, 24th, and the 1st of December, the 24th of November, and the 1st of December. When you go in, you have to register individually for each of the webinars, so you can select the date and time and register. By all means, register for all of them if you're interested. The next one will be next Wednesday, the 10th at 3:15 GMT, and we're going to have Hagen Bailey from Oxford and Yamuna Krishnan from University of Chicago, and they will cover the areas related to nanopores and DNA nanotechnology, particularly with at the interface with biology and medicine. So the second speaker today is Dr. Melanie Kah from University of Auckland in New Zealand. Unfortunately, Melanie is not able to be with us today because of, first of all, for personal reasons, but also because of the fact that she is in a time zone where at the moment is probably in the middle of the night. However, she was kind enough to send us a recording of a presentation. I would really highly recommend to stay online because what she has to say is very interesting. So Melanie is by background is studied agronomy and soil science, but and then she's had several positions at the University of York and in England, in other universities in England. She's been at University of Vienna. She's also been part of the CSIRO in Australia and is now moved to University of Auckland. And for a few years, she's been her interest is focused really on the use of nano materials in as fertilizer and as pesticides in agriculture. She's always, once again, she's had a very critical approach to the field, positively critical. So she's interested in the use of nanomaterials, but she's also aware of the limitations that are not always highlighted. In particular, she was the author of arguably the first paper that the Nature Nanotechnology published on nano-enabled agriculture, which was a long analysis about the let's say advantages and disadvantages of using nanomaterials in protection and in fertilization and pesticides. We compare in comparison to more bulk analogs. So unfortunately, obviously, she won't be able to answer any questions now, but as she says in her recording, and I can repeat it now, feel free to send questions directly, or you can send them to me, and I will pass them over. I will now play her video.
Hello, everyone. Thank you for joining this seminar today. It's Melanie Kah speaking from the University of Auckland in New Zealand. I'm really delighted to have been given this platform by the editorial board of Nature Nanotechnologies. Thank you very much for inviting me. I'd like to talk about the applications of nanotechnology in agriculture, and in particular, the area of plant nutrition and protection. I've been working on this topic for about a decade now, and there was not so much going on at the beginning. Activities have greatly accelerated recently, and there are lots of very exciting things going on at the moment, and this is what I would like to share with you today. My plan in the next 25 minutes or so is to start with a bit of context about agriculture and some of the current challenges that we're facing. I think it's important to first understand the problem, so then we can discuss about potential solutions that nanotechnology can bring. And then I would like to consider two aspects that are essential for the successful commercialization of nanoagrochemicals: validation of performances and regulatory compliance. And this will highlight some of the challenges that the field is currently facing. I will conclude with a couple of directions for the way forward that I hope will help nanotechnology to have some positive impact on agriculture, as much of a positive impact as possible on end users, which includes farmers, but also consumers of produce like you and me. So I would like to start pretty broad, and I thought a good starting point was the United Nations Sustainable Development Goals that have been developed in 2012, I think. Some of those objectives are about eradicating hunger and poverty, and to achieve some other important goals, including making agriculture more sustainable. The current global population is 7.8 billion people, and is projected to grow to 9.8 billion by 2050. And if we consider diet transition towards higher consumptions of meat, fruit, vegetables relative to consumption of cereals, feeding humanity is estimated to require at least 50% increase in the production of food relative to the level in 2012. And this is very often how papers presenting nanoagrochemicals start, with a rationale based on the need to increase global food production. There's no doubt that productivity of agriculture needs to increase, but how this can be achieved in a sustainable way is really uncertain at the moment. This graph shows what has happened over the last century. Yields have increased, but the demand has increased a lot as well. And this is why this curve is plateauing and even decreasing at the beginning of the year 2000s. Yields have increased mainly through what we call the Green Revolution, which included the introduction of mechanization, the introduction of new varieties, and the extensive use of irrigation and agrochemical. Yields are not increasing as fast as they used to. Demand is increasing, which leads to food insecurity in many parts of the world. This is what is represented here. We also see the resilience of crop declining here. This is what this curve is representing, for instance, as a result of climate change, soil degradation, or the extensive use of monoculture. And we can see also the environmental impact of agriculture increasing over time. And this is mainly associated with very low efficiency of many of those practices. So those three indicators suggest that we may be at the end of the Green Revolution, transitioning to what many call the agri-tech revolution. So the objectives are slightly shifting from just a purely productive system. And agri-tech revolution is rather aiming at developing more sustainable, more efficient, and more resilient agricultural system while promoting food security. This agri-tech revolution is likely to be fueled by a range of different technology, information technology, new methodologies such as gene editing, for instance, as well as new material. And this is where nanotechnology comes into place, because engineered nanomaterials are often presented as an ideal platform to achieve some of those goals. The size of nanomaterials, typically defined as below 100 nanometers, allows nanomaterials to cross some biological barriers that cannot be crossed by larger materials. They may be translocated from one part of the plant to another. Their structure, their surface chemistry can be modified to provide specific properties and functionalities that may be needed at specific locations within the plant soil system. And this makes engineered nanomaterials really, really attractive in this context. If you would like to get an overview of what nanotechnology can do for agriculture, I would recommend looking at an insight published in 2019 in Nature Nanotechnologies. It's a collection of papers that includes examples on how nanotechnology can help modifying plants to increase the efficiency of photosynthesis or the use of water. What I would like to focus on today is agrochemicals, and there are a couple of reasons for that, but one of them is that it is the area that has so far received the most attention up to now. That is the most advanced level of development. On this graph, you can see the number of patents that have been launched since 1990. And we can see that the number of patents is increasing exponentially. Some nanoagrochemicals are already commercially available. Some regulatory agencies indicate that they are receiving a growing numbers of applications for product registration. So this is a field that has been moving quite fast and far up to now. So what is a nanoagrochemical? There's currently not strict definitions for nanoagrochemicals, neither in the scientific or regulatory context. So current boundaries are pretty loose, and they may include products whose size is smaller than 100 nanometers, but we often also deal with objects that rather belong to the microscale, that have been designed with nanotechnology or that contain nanoparticles. The most important, from my perspective, is to evaluate whether those agrochemicals have been developed using nanotechnology to design more intelligent agrochemicals. And the whole idea here is to try and decrease the risk of associated with current practices and increase the benefits to overall contribute to the more sustainable production of healthier food in sufficient quantity. So we're going a little bit beyond the productivity focused objective and also look at sustainability and healthy aspects. So now I'd like to have a closer look at current practices. What has allowed the increase in yields over the last centuries? A lot to do with the extensive use of irrigation, plant nutrition, so the extensive use of fertilizers, and plant protection, so the use of pesticides to protect crops from fungal disease or insects or competing weeds. It is estimated that without those practices, production could decrease by about 40%. At this point, I think it's interesting to consider a concept that is called the maximum yield potential. It's basically the maximum yield for a given crop that grows without any limitation from water, nutrient, or pressure from pest or disease. In some regions in the world, yields have reached about 80% of this maximum yield capacity. I don't know, corn in the USA, for instance. And it's not entirely sure whether we can go beyond this 80% when we consider the uncertainty associated with variability of field conditions, variability in soil, variability in climate, for instance. On the other hand, in other regions in the world, yields are still less than 20% of the maximum yield potential. An example would be corn, again, in some regions of the sub-Saharan Africa. And these often corresponds to regions where food insecurity is the highest. So in these cases, yields could be greatly improved with existing technology, the applications of irrigation, fertilizers, or pesticides, but they remain largely not applied due to economic reasons. So in these areas, the challenge is to provide affordable and accessible tools that address the main factor limiting yield. And this is very different to other parts of the world where those tools are already extensively applied. So I think it is important to distinguish different contexts, those different areas that are facing different challenges. At this point, you may think that the solution to give food where people need it the most is simply to make sure that irrigation, fertilizers and pesticides are made available and used extensively everywhere. The problem is that it's not only an economic issue. There are also great concern associated with these practices because they remain highly inefficient. So for instance, irrigation efficiency very often is below 50%, meaning that the water dedicated to irrigation is not used by the crop. And it's particularly concerning when about 80% of the total fresh water globally is dedicated to irrigation. So irrigation, in other words, is a very important driver of water scarcity. If we have a closer look at the low efficiency of fertilizers, it's been estimated that conversion efficiency from synthesis to the farm gate is not higher than 10%. And this is followed by great losses after the applications of fertilizers in the field, either by volatilization or leaching. And this leads to great issues of water contamination, eutrophication of ecosystems. And something very similar occurs also with plant protection products or pesticides. It's been estimated that according to the mode of application, between 10 and 75% of those pesticides applied in the field are lost. They don't reach the target, but they contaminate nearby water resources, they may accumulate in soil, they may end up as residues on the food produce. And this is highly undesirable, especially because pesticides are often toxic substances. They've been designed to trigger biological responses, and we don't want them to be spread in the environment or end up in our diets. So if nanotechnology could increase the efficiency of irrigation, plant nutrition, or plant protection products, there would be a great environmental benefits, but not necessarily an increase in yield. So the most common objective of current nano agrochemicals is to tackle the weaknesses of current products. If we have a look at traditional approaches to crop nutrition and protection, we can see three key areas of applications for nanotechnology. First one is to try and achieve a higher application efficiency through the preparation of more stable suspension, for instance, or the applications of the product to a more precise target area. The second area of interest is reduced losses, unwanted losses. So for instance, if a pesticide is photodegradable, we may use a nanotechnology to make it more resilient or more persistent, or we may want to reduce transport of the pesticide to non-target areas, so limiting leaching to groundwater, for instance. And the third area is using nanotechnology to improve biointeraction, so improving the uptake of substance by a target crop, or also there's a lot of work going on for a more targeted spatial and temporal delivery. So it can be considered as a component of precision agriculture when the right amount of substance is released at the right place and at the right moment. And this has a great potential to increase the efficiency of currently used agrochemicals. So these were rather traditional functions, looking at improving current products, but nanotechnology has been also considered for novel functions that may be enabled by nanomaterials. These are typically less developed, but they are very exciting because they imply novel approaches to improve plant growth. So the three first examples I wanted to mention are looking at the applications of nanoparticles to improve crop resilience or crop quality. The first one looks at exploring the use of plant nutrition by the application of nanoparticles of zinc, copper, or sulfur, so that the plants become more resistant to pathogen infection. So I think this is really about recognizing and taking advantage of the strong links that exist between plant protection and plant nutrition, which is very interesting. There's also some work done using cerium or selenium nanoparticles to increase plant resilience, not to pest, but to more general environmental stresses such as drought, salinity, or temperature. And the third area is to look at biofortification. This has been achieved with the applications of nanoparticles of zinc or copper that fortify the produce in those micronutrients that are subject to deficiencies in many parts of the world. For those three examples, the mechanisms by which the nanoparticle increases the resilience of the quality of the produce are not yet always fully understood, but there is a lot of research going on the topic at the moment to try and underpin the mechanisms involved and try and explore them further. The two next functions that I wanted to mention today, they have received relatively lower attention so far, though I think they are really promising, so they are worth mentioning. The first one looks at nanotechnology in the area of sensing. There's been a lot of discussion on the use of nanosensors to detect pathogens, water, or the nutrient status in the field. And I think the idea is really real-time monitoring of the plant growth conditions and the possibility to respond very quickly to those. And this is highly attractive because, again, this would greatly increase the efficiency of irrigation, fertilizers, and pesticide use distribution across a field. I don't think we are quite there yet because there are great challenges to implement those sensors in the field. There are also challenges associated with the sensitivity to specific analytes once your nanosensors are deployed in the real world, in the real field. So the number of studies are relatively low at the moment, but I expect more work in this area is going on. Another area of interest is to use nanomaterials or nanoparticles to improve soil structure and soil health. So for instance, the use of nanoclay, nanozeolites that can modulate water retention, the use of zinc or copper oxides that can increase microbial activity that is beneficial for the growth of certain plants. Again, this research is at fairly early stages of development, and they need to be assessed more thoroughly at the field scale and against existing solutions. But I find them really, really interesting. Now, I'd like to have a look at the type of nanomaterials that have been considered to achieve those functions. And there is an incredible diversity of materials discussed in the literature, which means that it's a fantastic playground for researchers, but also a little bit of a nightmare for regulators that have to assess the safety of all those products. We'll talk about this in a minute. I would like to divide all those materials into two main groups, basically based on their complexity. The first, or what I call the first generation here, comprise engineered nanomaterials that have been considered in other sectors and that have been studied over the last 10, 20 years. These include carbon nanotubes, metal oxides, fullerene, quantum dots, for instance. And I mentioned a number of functionalities that those nanoparticles may have in the context of plant nutrition and plant protection. The second generation of nanomaterials is more complex in the sense that they very often combine different ingredients, different structure. They're more sophisticated particles that very often aim at delivering active substance that is either existing, so fertilizer, nitrogen, or pesticides. A number of novel active substances are also considered in this context, such as RNAi, for instance, which opens a whole new field of consideration for plant protection. So I've got here a couple of examples of these more complex nanostructures. Nanocapsules made of a range of natural or synthetic polymers is discussed a lot. Hydrogel, porous, hollow silica with some gates that could open to release active substances, virus capsides, graphene oxides, among many others. So with this overview, I think it's quite clear that we should not consider nanoagrochemicals as a single category of products. We need to consider a variety in terms of the wide range of functions that those nanomaterials can help us achieve, whether it's improving the delivery of a pesticide in time and space, or aiming at biofortification to tackle nutrient deficiencies. And the second aspect is also to consider the great variety of materials we are dealing with. These come with different costs, with different potential issues with safety, that we really need to consider when those may be applied in the field. So at this point, we discussed important challenges faced by agriculture, including the need to increase productivity, quality, sustainability of agriculture. And there is plenty of promising research suggesting that the use of nanomaterials can help achieving some of those goals. So how do we get those nanoagrochemicals from the laboratory to the market and to the field? I think there are two key aspects to consider that should probably be considered a little bit early on in the research and development process. The first one is a comprehensive validation of the performances of those nano-enabled solutions against conventional solutions. And the second one looks at regulatory compliance. So I'd like to discuss those two aspects in a little bit more details in the next slides. So let's have a look at performances to start with. As a general rule, a new agrochemical needs to improve something, efficacy, productivity, cost saving, but about 20% to be competitive on the market. And the metric that is used really depends on the agrochemical function and the desired benefit that it's going to bring. A couple of years ago, we have, with a group of other researchers, looked at studies available in the scientific literature that compared the efficacy of nanopesticides relative to conventional formulations. So one indicator for efficacy of pesticide is to look at how toxic it is to the target pest. A first finding from this research is that we only identified 14 scientific papers, which is not many considering, even though it was 3 years ago, considering the number of papers presenting nano-enabled pesticides. We also know that most of those studies were carried out in the laboratories. The relevance of field condition is not always obvious. On this graph, we can see the ratio of efficacy reported for the nano pesticides relative to the non-nano or conventional pesticides. So basically a point that would fall on this one line here would indicate similar efficacy for the nano and conventional pesticides. So this box plot shows that in some instances, some nanopesticides may have up to 1 order of magnitude higher efficacy compared to the conventional pesticides. But the median indicates that we are closer to 20 or 30% in general, which would be competitive on the market, provided those results hold under field conditions and that costs are not prohibitive. Comparisons of performances are also available in company websites, patents, but we're all aware that many reports are not publicly available. And for those reports that we manage to access, it's quite interesting to see that the metrics that are used in those reports, and very often field studies in this case, are not necessarily those reported in the scientific literature. So for instance, nanoagrochemicals may allow farmers to simultaneously apply pesticides and fertilizers together, saving costs and time, but not necessarily increasing yields. So I think it shows somehow some disconnect between what is reported in the scientific literature and what farmers are interested in. And that would be nice if more bridges existed there. The second point that is really important to consider when evaluating performances is the economic viability of the nano-enabled or nanoagrochemicals. It's particularly important because agriculture is typically fairly low profit margin industry. So we need to make sure that the nanoagrochemicals are economically competitive relative to existing solutions, can have 20% increase, but if the extra cost is 50%, it's simply not worth it. So this may be very context dependent as well. We cannot directly compare higher margin crops in the Western world, wine growing, for instance, with staple food production in areas where barriers to higher productions associated with political reasons or corruptions. So I think overall what is needed there is a more balanced analysis of social, economical and environmental gains to really fully capture a realistic evaluation of the performances that the nanoagrochemicals can achieve in a longer term and a more global context. Regulatory compliance is also something that should be considered very early in the research and development process. And it's particularly important, I think, for pesticides, because before being placed on the market, pesticides need to meet a number of safety criteria established by regulatory agencies. And these concern both ecological and human health aspect. And they are very stringent and the process is very complex. It may take 10, 15 years to actually convince regulatory agencies that a product is safe, because these agrochemicals are applied in the open environment. So if we compare nanoagrochemicals to nanopharmaceuticals, we have to deal with something that is somehow much more complex. For nanopharmaceutical, exposure is relatively well defined. We know that someone is going to take a certain dose, and exposure is limited to one type of organism, the human body, for instance. For agrochemicals applied in the open environment, there are multiple pathways of exposure to many different types of organisms. So for instance, if we first have a look at human exposure can happen during the preparation of the agrochemical, during its application, but also post-application during the harvest up to the consumption of the produce. During the and after the application of the pesticide in the field, this agrochemical is likely to come into contact with multiple organisms, including the target organisms, but also many non-target organisms, birds, bees, soils, aquatic organisms. And we want to make sure that all those non-target organisms are not suffering from the applications of agrochemicals. There's been extensive research looking at the safety of nanomaterials, identifying possible and desirable effects associated with their use. But most of this work focused on the first generation engineered nanomaterials, so relatively simple metal or metal oxides. Very little research is currently available for the more complex structures that I described a couple of slides ago. Knowledge remains also really limited for conditions that are relevant to agriculture when we talk about the intentional applications of relatively large amount of nanoparticles in the open environment. The current regulatory framework for agrochemicals and pesticides in particular is really sophisticated, but it does not always capture potential nanospecific behavior and characteristics, and adaptations may be required at different stage of the assessment. We end up very often concluding that this has to be done on a case-by-case basis, which is really challenging for regulatory agencies. Large part of my research is actually looking at those aspects, and we are trying to help both developers of nanoagrochemicals and regulators to assess the new risk in a fair way. Because one tendency may be to require a lot more data and understanding for nanoagrochemicals relative to conventional products. And I think it's very important to remember that the use of conventional agrochemicals is always associated with a certain degree of risks. And currently, their use is associated with really unacceptable damages to the environment. So again, I think comparing nano agrochemicals in terms of performances, but also safety, to compare them to current practices is really important. What are examples of the new risks that may need to be considered with nanoagrochemicals? For instance, we can think again about the potential advantages of nanoagrochemicals compared to current one in terms of application, reduced losses, or improved bio interaction. So could those changes be affecting the risk profile of pesticides in unintended ways? Yes. For instance, if pesticides is better uptaken by the target organisms, it may also be better uptaken by the non-target organisms. If a nanoformulation changes the way the pesticide is sticking to the leaves of a plant, and this is the way that efficacy can be increased, this may also mean that the amount of residues in the food produce is increased as well. So I think it's really essential that we can measure those changes and compare exposure and toxicity of nanoagrochemicals to conventional produce so that we can assess in a fair way the new benefits and the new risks and see whether they counterbalance each other. Because again, the objective is really to reduce the risk and increase the benefits we are getting from those agrochemicals. Well, this brings me to my last slides. I'd like to conclude with a number of thoughts. I hope that I managed to illustrate how agriculture is currently transitioning from the green revolution to the agri-tech revolution that aims at improving the efficiency, resilience, and sustainability of agriculture. So a shift in focus, and I have no doubt, many others have really no doubt, that nanotechnology will contribute to this transition. The area of plant nutrition and plant protection has received a lot of attention up to now, more than other potential applications of nanotechnology in agriculture. And there is a great variety of nano solutions that has been proposed in the scientific literature, and some look really promising. However, there is still a lack of mechanistic understanding and critical comparison with existing products, and in particular at the field scale. So more work is definitely needed in this area to bring those products closer to the market. I think there is also a need for more disciplined conversions to design and evaluate products that fit within the constraints of the global agri-food sector, whether it is in terms of usability, costs, regulations, or also consumer acceptance. I haven't mentioned this, but we have to make sure that users, farmers, and consumers are happy to have nanotechnology used for food productions. And you know, we have to consider risk of rejection based perhaps on memories of other technologies that have been introduced in the past, such as genetically modified organisms. So this needs to be really considered very carefully, together with usability, cost, regulations. The overall objective is really to make sure that we are not shifting a problem from one place to the other, but really reducing the problem. And eventually, this may be about more transdisciplinary approaches where end users are taken on board earlier so that nanotechnology can be used to solve the problems that users are facing in different contexts, and providing solutions that fit within the many constraints that exists. A final thought is going to the global scale. I think it would be really great to see more work towards a more equitable use of technology broadly. I'm thinking of farmers in developing countries where yields are still very low relative to developed countries. These are the areas where demand for food is growing fast and access to technology is currently very often limited. So really would be fantastic to see technological solutions to become more successfully implemented in those places that basically need them the most. This brings me to the end of this seminar. I hope you have enjoyed it. Thank you very much for your attention. Please do get in touch if you have questions or comments. Here's my email, and that's it for today. Thank you. Bye-bye for now.
And indeed, I'd like to thank you all for attending this webinar. I'd like to thank Manny and Melanie for their great contribution. As Melanie mentioned herself, please do send her any questions you may have or send them to me. I'll pass them over. And I will like to say goodbye for today. And I hope that you have enjoyed it. And I hope that you will join us next week for another interesting webinar. Bye.